Hello all, welcome back to Climate Dynamics. In today's lecture, we're turning our attention towards the fully coupled Earth system, in particular, the atmosphere and ocean and how these two components of the system interact with one another. Today's lecture will be on climate oscillations. The corresponding reading is Marshall and Plum, chapter 12.1. In this section, we're going to define teleconnection, Arctic oscillation, North Atlantic oscillation, Atlantic multidecadal oscillation, Pacific decadal oscillation, and Indian Ocean dipole. The key questions we will answer are, what are the typical timescales of the Earth system? What are the primary teleconnection regions of the world? And what regional and global patterns are expressed by these teleconnections? Alright, let's get started with a discussion of the timescales of the Earth system. Recall from our very first lecture in this class that the major components of the Earth system are the atmosphere, the hydrosphere, the land and land surface, the cryosphere, and the biosphere. Throughout this class, we've primarily focused on the first two reservoirs, that is, the atmosphere and the ocean. Hopefully you've learned that these two are both very similar and very different from one another. The atmosphere is made of a compressible fluid and has its own set of dynamical equations that govern its motion. The ocean, on the other hand, is made up of a largely incompressible fluid, and it is governed by parameters such as temperature and salinity. We have seen the atmosphere responds very rapidly to external forcing. The ocean, on the other hand, has very slow current velocities and tends to respond very slow, particularly at depth. So let's delve a little bit more into understanding those timescales. Consider the following question. How do the ocean and atmosphere act in response to temperature change? Recall from our second lecture that the energy balance in the Earth system implies that we must have no more energy leaving the system than we have energy coming in. However, we can exchange energy between the components of the Earth system. Effects such as greenhouse gas emissions are responsible for redistributing that energy in the system, leading to near-surface cooling. We already know that the ocean has a much greater capacity to store heat than the atmosphere, and consequently it has a role of damping out climatological changes. That is, it tends to mitigate some of the effects from near-surface warming induced by, for instance, greenhouse gas emissions. So if the atmosphere becomes too hot, then excess energy will tend to be stored in the ocean. In some sense, the ocean, having its high heat capacity, can act as a reservoir for that excess energy. Similarly, if the atmosphere becomes too cool, then the ocean will naturally release energy. One can describe this quantitatively using a simple thermal adjustment equation. On the left-hand side of this equation, we represent the thermal adjustment of the ocean, which is the change in temperature of the ocean with respect to time. It has a constant of proportionality, which is the heat capacity of the particular region of the ocean that we're interested in. The change in temperature within this region is governed by two processes. One, a relaxation, which is representative of, for instance, radiative emission and latent heat fluxes from the ocean. That has a tendency in order to draw down the temperature. That is balanced by an input of energy, known as the net air-sea flux. You notice that the change in temperature with respect to time is equal to zero when the thermal emission is balanced by the net air-sea flux. If we set the air-sea fluxes to zero, then the ocean will naturally cool over time. That is, radiative emission and sensible and latent heat fluxes will basically drive the temperature of the ocean down. If we solve this system, for the case of Q net equal to zero, we observe that the solution is simply a decaying exponential. The e-folding time associated with that exponential, that is, the amount of time required for the temperature to drop by a factor of 1 over e, will be given by gamma O divided by lambda. Thus, this factor, gamma O, governs the time scale of cooling associated with the ocean. Alright, let's try to calculate this gamma O. It is essentially a heat capacity of a slab of ocean. So gamma O is equal to the product of the density of the ocean water, the heat capacity of that water, and the associated layer depth. Here the density is the reference density taken as simply 1,000 kilograms per meter cubed, and the heat capacity of water can be obtained from a lookup table. The layer depth depends on how much of the ocean you're considering in this analysis. If you only consider the mixed layer, which is in contact with the atmosphere because of turbulent processes over very short timescales, you would effectively choose a layer depth of about 100 meters. If you wanted to consider the whole ocean, so you want to consider, for instance, how long it takes the whole ocean to cool off, you would instead choose a layer depth of about 5 kilometers. Correspondingly, the heat capacity of a slab of atmosphere can be denoted by gamma A, and it's equal to a mean layer density times the heat capacity at constant pressure times the vertical scale height of the atmosphere. All of these quantities we've had experience with previously in this class. The mean layer density we're simply going to take to be the near surface density, so we'll set that equal to 1 kilogram per meter cubed, acknowledging that it does drop substantially as one goes up in altitude. We can also choose the heat capacity at constant pressure to be 1.007 times 10 to the 3 joules per kilogram Kelvin, and we choose the vertical scale height as we calculated earlier in this class to be about 8 kilometers. So once you perform that calculation, you will then get approximations for the heat capacity of both the slab of ocean and the slab of atmosphere. Comparing these two, one finds that, for instance, if you only consider the oceanic mixed layer, then you still get a heat capacity that's approximately 50 times that of the atmosphere. This demonstrates immediately that the ocean is a much greater reservoir of overall heat. If you consider the whole depth of the ocean, the ratio of these two parameters is instead 2,500. So, as you can see, the whole ocean itself essentially contains approximately 2,500 times as much energy as the troposphere of the Earth. If we use an adjustment rate of about 15 watts per meter squared per Kelvin, taken from observations, then what we find is that the adjustment timescale for the mixed layer of the ocean is about 322 days. That is, cooling down the mixed layer of the ocean by a factor of 1 over E would take about 322 days. So obviously it's a very slow process overall. Adjusting the whole ocean takes about 1,000 years. This is in part because of the slow circulation that occurs in the abyssal layer as well. So we've already seen that the ocean is an excellent buffer of energy. How is this calculation different for the land surface? Well, we can perform effectively an analogous calculation for land, here taking density of rock, heat capacity of rock, and a height of rock, where the height is again taken to be approximately the region of the land surface that is in contact with the atmosphere. So how does this compare? Well, the density of rock will be a little bit higher than in the ocean, certainly. The heat capacity is more or less proportional. But where we see the biggest change between the land surface and the ocean is really in this H parameter. Namely, there is not much of the land surface that is in contact with the atmosphere, whereas the ocean has a deep mixed layer and turbulent action that sustains that deep mixed layer. The land surface only has perhaps a 10 centimeters to a meter or so that can be considered to be in contact with the atmosphere. Consequently, this H parameter is much smaller in the land surface. So, the heat capacity of the land surface is much smaller than in the ocean, and we see that the land surface then responds much more quickly to temperature changes than the ocean does. This is then responsible for that inhomogeneity that we've discussed earlier in this class, namely that the land surface tends to warm up and cool down much faster than the ocean. Besides thermal adjustment, there are many other processes and features of the Earth system whose timescales we wish to understand. In the atmosphere, the overall response time to heating is typically on the time scale of months. The typical spin-down time of wind in the absence of forcing is days. That is, if we were to shut down, for instance, external heating from the sun, we would find that wind speeds would slowly reduce, and that would take only on the order of days for them to do so. The frontal system lifetime, that is, these large-scale systems that propagate through the mid-latitudes, typically also have timescales of days associated with them. The convective cloud lifetime, which is typically on spatial scales of 100 meters to kilometers, only has hours associated with it, whereas the timescale of the upper-level winds is more on the order of days. In the ocean, the response time of the upper ocean to heating is on the order of months to years, but the response time of the deep ocean to atmospheric changes can be on the order of decades to millennia. We've already seen in our discussion of the oceans that CFCs, which are introduced in the atmosphere, take decades to millennia in order to propagate through the depths of the ocean. This is again due to the very slow circulations that occur in oceanic depths and the fact that once you get below the thermocline, there's very little influence from the atmosphere. The ocean eddy lifetime is on the order of months, ocean mixing in the surface layer is on the order of hours to days, and the time for a typical ocean current in order to cross the ocean is on the order of a decade. So, again, a very slow process. Contrasting these two, it is very clear that the ocean adjusts much more slowly than the atmosphere. We can also look at the cryosphere, the land surface, and the biosphere. We know that snow cover, for instance, exists on a timescale of months, that is, it's roughly seasonal, and analogously with sea ice. Although with sea ice, we can of course have buildups of sea ice that are associated with longer processes. Glaciers take decades to centuries in order to build up, but as we've seen recently, they can be destroyed over much shorter time periods if you crank up the thermostat. Ice caps, on the other hand, take centuries to millennia. That is, they accumulate over a very long period of time. However, again, destruction of these ice caps can occur over short timescales. The land surface, as we discussed earlier, has a very short response time to heating. It takes only on the order of hours for temperatures on the land surface to adjust to changes in external forcing, such as radiative forcing. Analogously, the response time to vegetation to oppose excess evaporation is also on the order of hours. And soil moisture response times are on the order of days to months. In the biosphere, ocean plankton's response to nutrient changes can take on the order of weeks, but recovery time from deforestation can take years to decades. Alright, now that we've talked about some of the timescales of the Earth system, let's turn our attention to some of the large-scale climate oscillations that exist. Climate oscillations, which refers to periodic behavior within the global Earth system, are closely connected with teleconnections. Teleconnections are relationships that occur between climate anomalies at large distances, typically on the order of thousands of kilometers. Major teleconnection centers of the world are known for propagating their influence globally and influencing the climate far away from those teleconnection centers. An understanding of these teleconnections is important to understanding connections within the climate system and propagation of information over large distances. Many of these teleconnections between the tropics and extratropics are understood primarily through the propagation of linear planetary waves upon a 3D seasonally varying background state. However, the investigation of the actual mechanisms by which these teleconnection centers propagate information globally is outside the scope of the current class. The teleconnection patterns that we'll be discussing in this class include the Arctic Oscillation, also known as the Northern Annular Mode, the North Atlantic Oscillation, the Atlantic Multidecadal Oscillation, the Pacific Decadal Oscillation, and the Indian Ocean Dipole. The El Niño Southern Oscillation is important enough that it deserves its own lecture, and so we'll discuss that in the next class. Alright, let's get started. So the Arctic Oscillation is the first teleconnection pattern that we will be discussing. The Arctic Oscillation is an atmospheric circulation pattern over mid to high latitudes of the northern hemisphere, which varies over time but has no particular periodicity associated with it. Its most obvious characteristic is the oscillation in the location of the mid-latitudinal jet stream. During the negative phase of the Arctic Oscillation, the mid-latitude jet stream tends to be more windy. During the positive phase, it tends to be more laminar, or more straight, confined to a narrow band of latitudes. The Arctic Oscillation regulates the degree to which Arctic air penetrates into the middle latitudes. It is generally one of the more predictable oscillations over shorter timescales and hence lends predictability over periods longer than the typical forecast window of 7 to 10 days. During the negative phase, we have a tendency for more Arctic air to penetrate farther south. Consequently, this can lead to cold conditions in more southern latitudes than they would appear typically. During the positive phase, we have more isolation of that Arctic air. Typically, this is associated with larger temperature gradients around the location of the jet stream, but also a tendency for that Arctic air to not penetrate into farther southern latitudes. The negative phase in particular is associated with the transport of this frigid air far south. In February 2010, when the Arctic Oscillation reached its index value of minus 4.266, which was the record for the time, the U.S. received 3 separate historic snowstorms because of the transport of this cold air. During the positive phase, the higher pressure in the mid-latitudes tends to drive ocean storms farther north, and tends to bring wetter weather to Alaska, Scotland, and Scandinavia, as well as drier conditions to the western U.S. and the Mediterranean. During this phase, frigid winter air does not extend far south into Middle America and tends to be isolated within the Arctic region. Here are some of the meteorological patterns that are associated with the Arctic Oscillation. Again, during the positive phase, we have a very strong jet that tends to isolate cold Arctic air in the higher latitudes. This is then associated with a stronger storm track, and consequently storms that propagate across the Atlantic, bringing warm and wet conditions to northern Europe. Because the storms are also farther north, southern Europe tends to be drier. This pattern is also typically associated with stronger trade winds. During the negative phase of the oscillation, we have a very windy yet weak jet stream. Consequently, there's more opportunity for cold Arctic air to penetrate southwards, and that brings cold conditions to both Middle America and to Central Europe. However, because of the weaker trade winds, we also then have typically storms that can propagate into southern Europe, bringing wetter conditions through that region. On the left-hand side of this plot, we see the temperature anomalies associated with the Arctic Oscillation, and on the right, we see the precipitation anomalies. Note that these plots are both made looking directly down on the North Pole. What we see in the temperature anomaly plot is that during the positive phase of this oscillation, we have colder conditions isolated in the Arctic. That is, we see cold weather in Greenland and in northern Quebec in Canada. But it's associated with warmer conditions farther south. So much of Europe, central Russia, and the lower latitudes of the continental United States experience warmer conditions during the positive phase of the Arctic Oscillation. The precipitation fields associated with the Arctic Oscillation indicate wetter conditions through Middle America, but drier conditions through southern Europe during this time. Here's a time series of the extended December, January, February, March winter season, showing the Arctic Oscillation indices. Red in this plot corresponds to positive phases of the Arctic Oscillation, and blue corresponds to negative phases. As we can see, there's no obvious trend over this short time period. However, more recently, we have seen more instances of positive phase Arctic Oscillation. However, we also see very extreme negative phase Arctic Oscillation. In particular, the most extreme negative Arctic Oscillation value on record occurred in 2010. At this most negative monthly mean value, this was associated with 3 separate historic snowstorms, as mentioned earlier. Alright, let's turn our attention to the North Atlantic Oscillation. The North Atlantic Oscillation is very closely connected with the Arctic Oscillation, and is also associated with the windiness of the jet stream. The North Atlantic Oscillation is a weather phenomenon in the North Atlantic Ocean of fluctuations in the differences between atmospheric pressure at sea level between the Icelandic low and the Azores high. Obviously, since it's associated with these fluctuations in sea level pressure, it is also closely connected with the jet stream via geostrophic flow relationships. The North Atlantic positive mode is shown in the top right here, and the negative mode shown in the bottom left. The positive phase of the NAO is analogous to the positive phase of the Arctic Oscillation, in that both have a fairly laminar jet stream, again confined to a narrow band of latitudes. Whereas the negative mode is again analogous to the Arctic Oscillation in that it corresponds to a windier jet stream. During the positive phase of the NAO, we typically have cold conditions in Greenland and northern Canada, as well as cool and dry conditions in southern Europe. These also correspond to warm conditions in the southeast of the US and warm and wet conditions through northern Europe. The negative phase of this mode is associated with warm conditions in northern Canada as well as less sea ice, and is associated with cold and snowy conditions along the eastern seaboard of the continental US. It's also associated with cool and dry conditions in northern Europe and warm and wet conditions in southern Europe. The NAO is again closely related to the Arctic Oscillation, but tends to be more regionally focused. If you look at the sea level pressure anomalies associated with both of these patterns, they are closely related but still not quite on top of each other. Here's the NAO index time series for the extended December, January, February, March winter season extending back to 1864. As we can see, it varies between both positive mode and negative mode. Alright, the third form of oscillation that we'll be looking at is the Atlantic multidecadal oscillation. This is a mode of variability occurring in the North Atlantic Ocean that is expressed in the sea surface temperature field. The period of the Atlantic multidecadal oscillation is about 50 to 90 years, with about 25 to 50 years associated with each component of the cycle. That is, typically it's in a positive phase or leaning towards a positive phase for about 25 to 50 years and then switches into a negative phase. This pattern was originally identified by Schlesinger and Ramankutty in 1994. However, there's some controversy about its real amplitude and if the methods for extracting the natural climate signal are valid. Nonetheless, the estimates peg the magnitude of this oscillation at about half a degree Celsius. This oscillation is strongly correlated with air temperatures and rainfall over much of the northern hemisphere. As one would expect, this multidecadal oscillation affects the northern Atlantic sea surface temperatures, which can then impact warming of the northern hemisphere. These warmer conditions can then impact evaporation, which can impact the amount of moisture present within the air. This multidecadal oscillation is also associated with the frequency of North American droughts, with the warm phase corresponding to more frequent and prolonged droughts, as well as the severity of Atlantic hurricanes. Typically, warmer Atlantic waters are associated with more intense hurricanes. In models, this AMO-like variability is associated with small changes in the North Atlantic branch of the thermohaline circulation. Recall from last time we discussed how the thermohaline is responsible for bringing warm waters into the North Atlantic, as well as being responsible for driving things like sea ice extent. The AMO then is closely connected to the variations that occur within the thermohaline. Here are monthly values of the Atlantic Multidecadal Oscillation Index, showing positive phase and negative phase. The departures here correspond to sea surface temperature departures, so positive values are warmer conditions in the North Atlantic, and bluer values are cooler conditions in the North Atlantic. This is obtained by taking the observed sea surface temperature record and subtracting off the long-term mean as well as the signal that comes from anthropogenic forcing, which would naturally give an upward trend associated with this profile. As we can see, we have extended periods of positive values of the AMO as well as extended periods of negative values. Here's the pattern associated with the Atlantic multidecadal oscillation. Again, during the positive or warm phase, we see much warmer oceanic conditions that extend far north to the Labrador Sea and to Greenland. Whereas during the cooler phase, we effectively get the negative of this signal. That is, we have cooler temperatures throughout the North Atlantic. It's known that there's a significant correlation between the Atlantic multidecadal oscillation and rainfall in Florida. As we know, during the warm phase, we have more evaporation from the ocean surface as well as warmer near-surface airs. Consequently, the atmosphere can hold more moisture and so will have a tendency to produce more precipitation. Since the climate of Florida is so strongly connected to that of the Atlantic Ocean, water resources in Florida are largely impacted by changes in sea surface temperatures within this region. It's known that for instance, lake levels in Lake Okeechobee can change by 40% between AMO extremes. That is, during the warm phase of the AMO, we typically have much more precipitation and consequently a higher level in the lake. During the cold phase, on the other hand, this is associated with less rainfall and more frequent droughts within the region. However, the warm phase also comes with more tropical cyclones, because those warmer ocean waters are again driving up the intensity of those storms. Alright, in the Pacific Ocean, there's a corresponding partner to the AMO known as the Pacific Decadal Oscillation. This is a robust, recurring pattern of ocean atmosphere climate variability centered over the mid-latitude Pacific Basin. This was originally named by Stephen Hare in 1997. During the warm phase of the Pacific Decadal Oscillation, the West Pacific cools and part of the Eastern Ocean warms. The opposite pattern shows up during the cool phase. The PDO pattern can actually be seen through much of the Pacific. Typical phase shifts in the PDO typically occur on a timescale of 20 to 30 years. That is, analogous to the Atlantic multidecadal oscillation, the PDO tends to exist within a certain phase pattern for 20 to 30 years before flipping to its other mode. The PDO is associated with the sum of several processes that have different dynamical origins, but is primarily caused by the interaction of both tropic and extratropic forcings. Here's the Pacific Decadal Oscillation Index observed back to about 1900. Here we again see positive and negative modes associated with the PDO, with a strong positive period occurring between 1920 and approximately 1945, followed by a negative mode period, and then in the 1980s picking up again in the positive mode. Recently, we've seen oscillations as well, as the mode shifts between negative to positive. Here are the sea surface temperatures associated with the Pacific Decadal Oscillation pattern. This is the positive mode, that is, it's associated with cooler temperatures in the western North Pacific and warmer temperatures in the coastal Pacific. This pattern actually looks quite analogous to the El Niño mode, that is, it's associated with warmer temperatures in the eastern tropical Pacific as well. However, the timescales associated with the Pacific Decadal Oscillation are much longer than those of El Niño. Impacts of Pacific Decadal Oscillation include both temperature and precipitation impacts. Here we see the impact on the 2-meter temperature or near surface temperature through the northern hemisphere. In Alaska, along the west coast of Canada and the west coast of the continental US, the positive phase of the PDO is associated with much warmer temperatures in these coastal regions. On the other side of the Pacific, we see cooler temperatures. This is simply because of regional forcing because of this temperature shift in the Pacific Ocean waters. However, there is a broader extent associated with these impacts as well. We see weak forcing that extends over much of the globe associated with the positive mode. The negative mode is analogous except with the sign flipped. Here are the precipitation patterns associated with Pacific Decadal Oscillation. During the positive mode, we see typically much wetter conditions occurring along the coast of Alaska, but drier conditions occurring in the Pacific Northwest. In California, we see typically wetter conditions associated with the positive mode. This has to do with how this positive mode is impacting the geostrophic flow and thus the storm track in the vicinity of the eastern Pacific Ocean. However, we again see some widespread impacts in the precipitation because of this shift in the polarity of Pacific Ocean sea surface temperatures. The last pattern we'll consider in this lecture is the Indian Ocean Dipole, also called the IOD. This is also known as the Indian Niño because it is very closely associated with the El Niño. It's the Indian Ocean pair, essentially, to the El Niño. This is an irregular oscillation of sea surface temperatures that occurs in the Indian Ocean. During the positive phase, the western Indian Ocean becomes warmer than the eastern part of the ocean. This pattern is reversed in the negative phase. There is an average of 4 positive-negative IOD events that occur during each 30-year period, with each of the events lasting around 6 months. The IOD is known to affect the strength of monsoons over the Indian subcontinent, as well as rainfall over Australia and East Africa. Here we see the Dipole Mode Index, which is used to quantify the strength of the Indian Ocean dipole. It is equal to the Indian Ocean temperature in the western Indian Ocean minus the temperature in the eastern Indian Ocean. Thus, large positive values are associated with warmer temperatures in the West Indian Ocean, and negative values are associated with warmer temperatures in the East Indian Ocean. Over the recent 2019 through 2020 season, the Indian Ocean experienced some of its largest values of the Dipole Mode Index. This was again associated with very warm temperatures in the western Indian Ocean. During this time, the suppressed precipitation that then occurred over Australia contributed to the devastating Australian bushfires that burned over this season. Simultaneously, heavy flooding occurred in East Africa, where warmer sea surface temperatures then contributed to increased convection and precipitation. Here's a depiction of what occurs during an Indian Ocean dipole positive phase. A large-scale circulation gets set up associated with these warmer conditions in the West Indian Ocean. Because the underlying sea surface temperatures are warm, they produce convection that dominates this region. A circulation then gets set up so that the air that gets convected upwards gets propagated eastwards along the equator and then sinks over the eastern edge of the Indian Ocean. This sinking motion or subsidence then suppresses precipitation in this region and is associated with cooler sea surface temperatures. This circulation set up during this positive phase then contributes to an increased chance of rain in Africa and a reduced chance of rain in Australia. During the negative mode, we basically see a reversal of this pattern, with wetter than normal conditions occurring over the maritime continent and cooler than normal conditions occurring over the western Indian Ocean. This is associated with a reduced chance of rain in Africa and an increased chance of rain in Australia. All right, that's everything for today. As discussed earlier, next time we'll be dedicating our lecture to the El Niño Southern Oscillation.